This is question number 7 from chapter 8 in the textbook. It reads, a grinding wheel, which is 0.35 meters in diameter, rotates at 2,500 RPM. The first question is calculate its angular velocity in radians per second. So I've made a little sketch here of the grinding wheel, and we're given the diameter, and we're asked to calculate its angular velocity in radians per second. So we need to convert units of RPM into units of radians per second. When you do this type of a problem, you should immediately recognize that RPM is a unit of angular velocity. So at this point, it requires a conversion. I'm going to use my trusty train tracks, and I will start first by writing 2,500 RPM as 2,500 revolutions over 1 minute. This allows me to treat each separate portion of this unit and convert the numerator separately from the denominator. So let's go ahead and do that. We will start up with our first conversion factor, which is 1 revolution is equal to 2 pi radians, if you remember your unit circle. And that allows me to cancel out the revolutions, and now if I were to stop there, I'd have units of radians per minute. I'm not quite done because I need to convert the minutes into seconds. My conversion factor will be 1 minute over 60 seconds. If I organize my conversion factor that way, the minutes cancel out, and I would now have radians over seconds, which is what I'm looking for. So when I multiply 2,500 times 2 times pi and divide that by 60, I end up getting 260 radians per second, which is the answer to part A. 260 rad per sec. Part B then goes on to ask for question number 7, what are the linear speed and acceleration of a point on the edge of the grinding wheel? That requires you to recognize that the linear speed, or something that we can call the tangential speed, is equal to the angular velocity in radians per second. That's critical. It needs to be in those units. And so I'm going to go ahead and draw that v tan vector right on the edge here. So I need to know the angular velocity in radians per second, which I now know from part A, and I need to know the radius of the wheel, which I can essentially get from the diameter, and dividing that by 2 would allow me to figure out that the radius in this particular problem is 0.175 meters, or 17.5 centimeters, 0.175 meters. Okay, so now that I know that, I can go ahead and plug in my angular velocity in rad per sec. That's 260. I figured that out from part A, and I'm going to multiply that by the radius, 0.175 meters. And when I do that, I get a tangential speed in meters per second. That's the kind of translational velocity. Technically, it's a tangential or linear velocity for part B of 46 meters per second. Oops. Part B is a bit tricky, the second part of part B, because it says it wants to know what the acceleration of a point on the edge of the grinding wheel is right here. And so in this particular problem, in a straight line along that tangent line, since it's spinning at a constant speed, there is no tangential acceleration on that line. There is a component of radial acceleration directed inward. And so it depends on what you're being asked. If you were being asked about tangential acceleration, the answer would be 0 because the edge of the wheel is moving at a constant velocity. If you're being asked about radial or centripetal acceleration, then you would need to harken back to some concepts from previous unit. In this case, we can recognize that there's an equation for radial acceleration, which is going to be omega squared times r. So now I can basically recognize that even though it's not accelerating in the tangential sense, there still is a center-seeking acceleration. So I'm going to take the 260 radians per second, I'm going to square it and multiply it by my radius of 0.175 meters, and that gives me a center-seeking component of acceleration for the second part of 12,000 meters per second per second. And you'll notice that these units here, both in meters per second, are what we would expect for tangential velocity, and in this case, radial acceleration in meters per second per second.